back to Calculus 1, October 29th, 2016. We're talking about graphing functions by hand. No more computer, no more software. It is just you and calculus and a pencil or a pen, whatever you use, or a tablet for some of you. So we know certain points from algebra. We know how to find x-intercept, y-intercept by setting x or y to 0. We know how to find domain and range. We know how to find minimum and maximum using the section 4.1. We also know through critical points. We also know how to find inflection points. We also know how to do first and a second derivative test to figure out increase, decrease, and concavity. So when we take all of this and put it together, it will give us a whole, and then vertical asymptotes, horizontal asymptotes. When we put all of this together, we get this picture of the function, and it's easy to graph at that point. So let's just write like a shopping list of things that we calculate, and then we put all of those on the graph paper, and we get the graph. So x and y intercepts, domain, you don't really need range, asymptotes, you have vertical, horizontal, slant. I don't know why I put a question mark there. We also know how to do the first derivative test, second derivative test. Now, first derivative test will lead into increase, decrease, and the second derivative test into concavity. Both of which can give us min-max. Well, we know that min and max occur at critical points. Critical points are found by setting the first derivative to 0. Maybe in some cases you will have to calculate additional points. So as you can see, half of this list is algebra and precalculus, and half is calculus. Well, actually, a third on each, right? Whatever. Graph y equal x squared, because we know. But we want to see all the aspects of this function, pretending that we don't know how to graph this. So I will start by x-intercept, where I set y equal to 0. So that 0 equals x squared, from where x is equal to 0, from where x is equal to 0, and we started with y equals 0, so 0, 0 would be the x-intercept. Now, if you ever get for either x or y intercept 0, 0, then the other one has to be also 0, 0, because that's the only place where x and y axes intersect. So if either one of these two calculations gives you 0, 0 origin, then the other one must also be at 0, 0. And that takes care of that. So now we have our x and y intercept. Now intercept could be that the graph of the function passes through or bounces off of it. So you can have a graph go like that, or the graph bounce off anytime you have the x-intercept. So we have to keep that in mind. Yes? There was a stretch? Oh. Next one is domain. Just make sure that the stream is moving. Yep. So in terms of the domain, we know that it is a polynomial, which implies all real numbers. So this is this double bar R. You can also write it as negative infinity to positive infinity. If you like to write more, it's okay. No asymptotes. Of any kind. And now we do the first derivative test. So we take that our function is x squared. We find the derivative, which is 2x. And we set that one equal to 0 in purple. We solve the equation, x equals to 0. And then f of 0 is also 0. So we see that there is a critical point at 0, 0. Those critical numbers, critical points, partition our number line x. And you are supposed to pick two test values in each of the regions that you get. So now to do the first derivative test, we say f prime computed at -1 is -1 squared, which is 1, which means what? Sorry, it's the derivative is 2x. So 2 times -1, which is -2, which is less than 0. And what does this first derivative tells us? What? Increase or decrease? So this is decrease. So I'm going to put the arrow like this above -1. So what do I have? First derivative test, you take the original function, you find its derivative, you force it to go to 0 because you want to find critical values, which is where min max is. Then we solve the equation, we find its y value, so we have x comma y, and this point becomes your critical point, which is either min or max. Then we make the partition, use all the critical points and asymptotes. We have no asymptotes in this case. So the only place where we cut is at 0. We pick two test points, and then we plug test points in the first derivative, and then we compute the first derivative. It works out to be less than 0. If the first derivative is less than 0, that means that the original function is decreasing. All right? We are going to repeat this procedure now on what do you call this one? Positive one. So we do the same thing, and we will find now that the function is increasing. So f prime computed at 1. It's called first derivative test because we are using these test points and the first derivative. And we have the increase. Once you have this, you can see that 0, 0 is a minimum, right? Because the function has to decrease and then increase. So let me just do the motion here. The function goes down, and then it goes up, and we know that at 0, 0 is a critical point which is either min, max, or inflection. So it goes down and then goes up, so that's how we know it's a minimum. So you have to finish this first, get the arrows, and then the arrows will show whether it's min, max, and then inflection as well. Second derivative test. We are taking second derivative, which in this case is just number 2. Number 2 is larger than 0 at all times. So for all x, second derivative is always positive, and when that happens, what's the conclusion? When the second derivative is positive? So conclusion is concave up for all x. Now concave up looks like that, right? Fair? So now we can graph. There are other things that you can look into, even function, odd function, using those formulas, symmetries. There are other points that could be made, but yeah, let's see what we can do. So we have our 0, 0. And we know it's a minimum. Now this is very important, guys, to understand. Look what I'm doing. It's a minimum, so I put a smiley face through it, okay? If you get that it's a maximum, you will put a frown. You have to start it off a little bit, right? And then you will just notice that the function is always concave up, so you can just finish it off into a parabola. You can also go and say it's decreasing first, and then it's increasing later, right? And as you can see, everything fits together to make a graph like this. Do not make a spike, because that will be absolute value, and it will be a wrong answer for this particular problem. So here is the graph going through 0. Now we all knew this, right? But this was done mainly to illustrate the principle of what we are going to do on far more complicated functions. So find the x-intercept, find the y-intercept. That's algebra. You set x equal to 0, y equals to 0, figure those out. Domain, right? Do you know how to find domain? Asymptotes. We should know that exponential functions have horizontal asymptote at, let's say, at x equals 0, sorry, y equals 0. Then we can have tangent function that has infinitely many vertical asymptotes. So these asymptotes also need to be known. And if you're not sure, well, you're using limit from your chapter 2, right, to find the asymptote, if you're not sure. And then we have the first and the second derivative tests, which are always done completely. And then we have at the end, if need be, compute extra points, maybe look into symmetry and other aspects that are, sometimes needed. Not always, but sometimes. Now, from lecturing standpoint, I'm done. We just need to do examples. These examples take a long time because there is a lot of calculations involved. So I just want to take a few examples from homework, from the textbook, and obviously you guys will work out stuff on my MATLAB and others. So f of x equals to 4x plus 4 divided by x squared plus 3. And this would be problem 20. Oh, and they are calling for technology here. Why are you calling for technology? I don't know, we'll discover it maybe. So I will suggest immediately taking the first and the second derivative on top, so it's always easy for you to go back and find where those are. So figure out the first and the second derivative while I eat the cookie. Called division of labor. I'm so used to being right here. Are you doing your quotient rule? No. Thank you. Logarithmic differentiation. Look, everything's done. Exactly. Everyone is like covering it now. No. No quotient rule. See, that's the purpose of the logarithmic differentiation. You learn that thing, you just look at it, you know the answer, you never have to do quotient rule again. You won't. Disposal of the evidence. Oh, it was never there. Cover it up. So logarithmic differentiation, we copy the same problem immediately, and then in parentheses we have what? 1 over x plus 1 minus 2x over x squared plus 3 done. That's the derivative. It's in the factored form already, ready for us to do work. So the first derivative is quickly 4x plus 4 divided by x squared plus 3 times, and then we have 1 over x plus 1 minus 2x over x squared plus 3. And they're done. Now you set it, well, do the second derivative then. I think they want you to use technology because the second derivative is going to be terrible. Right? Yeah. They cancel because this becomes the denominator, right? 4x plus 4 is the denominator, and the derivative of 4x is 4 on top. So this factor and cancel. There's a little bit of algebra there. Skip like a million steps, as we usually do. I skip like 7 steps each time. Fill in the blanks. What are you gonna do tomorrow, right? Going through these notes. Alright, so let me explain what I did, and then I hope you will actually try to untangle this. So I used the logarithmic differentiation because that's the easiest way to just look at it and be done. So whatever is in the numerator, it's going to be positive. Whatever is in the denominator is a negative term. Next, we copy the function that's always there, and then we take the ln is derivative of this divided by this. So the derivative of this is 4 divided by itself, but all the 4's cancel, so we get this first term. And then because it's the denominator, we have a minus. Derivative of this is 2x, goes on top, and x squared plus 3 is on the bottom. Now, I will use that first derivative to compute critical points and all of that, because it's in the factored form, and it should be easy to use. Then, I rewrite the first derivative because I want to avoid product rule for the second derivative. So what I do is I multiply this times 1, I distribute this one to both. But look, x plus 1 and x plus 1, if you factor 4, so they cancel. And I have 4 over this for the first term. For the second term, minus. I get x plus 1. Oh, I forgot the next there. What happened? Oh, the thing. Yeah. All right. I did the x squared, right? That's true, right? Minus 10. Oh, too late now. So there is an x that it's missing here. And now I take the derivative of this one, again, logarithmic differentiation, so copy it as is. Should say 8x over there. I'll put x right there. So 8x is plus 1. And then we take the derivatives. Derivative of ln of 4 or derivative of 4 is all 0, so we don't have to worry about that. Denominator, 2x over x squared plus 3 with a negative in front because it was the denominator. And then we're taking the derivative of the second one. We have minus. And now 8x. So 8x. That's just 1, right? So I need over here minus 1 and then minus the rest. Right? 8x.
Yeah, 1 over x. Couldn't you just, like, I don't know, take an easier one? You know, to use the second example? Because this is kind of a jump from, you know.
Easy. Look. We pick the second problem. We do this later, but I also have to remove the tick mark then. And you don't get your points back. X squared over x minus 2. The first derivative is, and then what do I have? That's a 2x, 2 divided by x, minus 1 over x minus 2. Awesome. That's the first derivative. Rewrite. First derivative for easy. Second derivative, well, should I say easy? So f prime is, these guys cancel, so 2x over x minus 2 minus x squared over x minus 2 squared. And then, you know what, we can go all the way with this one. X minus 2 on a common denominator. So we have that the f prime is equal to 2x squared, so x squared minus 2x over x minus 2 squared. So I found the common denominator. That's going to be 2x squared minus x squared is 1x squared, and then minus 2x. Awesome. Now we take the derivative of this, which is going to be, what do you mean by? Oh, that's a 2, not a 1. Then tick mark stays over there. I so want this 2 to be there. This is a 2. That's why. I looked at it as a 1. Awesome. Yay. So take that times the derivative of this would be 2x minus 4 divided by x squared minus 4x minus 2 over x minus 2. That good? Anyone? You take, yeah, that's good. So now That's the derivative. I like to put derivatives first so I know where to find them for later. X-intercept. Let's go algebra first. So we set y equal to 0, which means x squared minus x minus 2 needs to be equal to 0. When you cross multiply, you get x squared equals to 0. You get x equals to 0. So 0, 0. Now you know immediately that the y-intercept must also be at 0, 0, because that's the only place on the axis where both of them converge to a single point. X-intercept and y-intercept, if there is one. Domain. Wrong. So domain. Interrupted at 2. Because that's when denominator is 0. So domain must be negative infinity to 2, union 2 to infinity. Asymptotes. So asymptotes, we know we have horizontal, vertical, and slant. So for vertical asymptote, we set denominator equal to 0, and we get x equals to 2, so vertical asymptote is at 2. Horizontal asymptote, where? Anyone? Horizontal asymptote? Do what? At 0, right? Exponent on top is bigger than exponent on the bottom. Or you can say limit x goes to infinity of the function x squared divided by x minus 2 is 0. Oh no! Yeah, just no horizontal asymptote because the degree is higher. The degree numerator is higher than the degree on. See, as soon as I wrote limit, I saw that it was wrong. Memorizing rules, usually doesn't work. I said the wrong thing and I wrote the wrong thing, y equal to 0, and as soon as I wrote the limit down, I saw it was wrong. So the limit of x squared over x, right? Forget about these 2. They cancel down and just have x. When you plug infinity for x, you get infinity. So no horizontal asymptote, no slant asymptote. For slant asymptote, degree in the numerator has to be exactly by 1 more than the denominator. And there you go. That's done. Now we have first derivative test. Well, critical points first. We have that the first derivative is equal to, but we can use the other form as well, whatever. X squared minus 4x divided by x minus 2 squared. We set that equal to 0 here in purple. Is that screen in your way? Let's see. It's not just you, everyone in the line behind you. There we go. We set this equal to 0. This is the reason why you never care what's happening in denominator. As soon as you set it equal to 0, you do cross multiply, it will multiply into 0 and it goes away. So technically we only worry about the numerator, which in this case looks like this. We factor out x, we get this, and then x is 0 and x is 4. So at these two values, x is 0 and x is 4, you have either min or a max or inflection point. So you have to have something. We can quickly figure out what f of 0 is, which is 0, and f of 4, that's 4 squared over 4 minus 2, which is 16 over 2, which is 8. So I have 0, 0, and 4, 8. Those are the two critical points. Now, for the first derivative test and for our partitioning, it's very important. Look what I have. I have a partition at 0, I have a partition at 2, and I have partition at 4. So partition 0 and 4 are from critical points, partition at 2 has the vertical asymptote. So here, critical number, a vertical asymptote, and another critical number. So you know where the partitions come from. Now, we are picking -1, 1, 3, and 5, let's say, as test points. And we're going to see increase, decrease, and all of that. So first derivative computed at -1. -1 squared minus 4 times -1 divided by -1 minus 2, everything squared. The beautiful thing about this denominator is that it always gives us positive numbers, so we actually don't have to worry about computing denominator at all, because it is squared. Anytime you have just a square in denominator, which most of the time you should, it's because of the quotient rule, we get, in this case, 1 plus 4 divided by, look at this, positive number. I don't care what the values are. Larger than 0, I have increase. I didn't even want to bother adding 1 plus 4, because I know it's a positive value. That's all I care. Is the entire number positive for increasing or negative for decreasing? That's all I care about. Next one. Is 1. So f computed at 1, f prime computed at 1, which is 1 squared minus 4 times 1 divided by 1 minus 2 squared. Again, denominator will always be positive, but the numerator this time is negative because we have 1 minus 4 over positive value, which is negative value, divided by positive value, which is overall negative value, less than 0, so we have a decrease in here. Next, f prime of 3. So that's going to be 3 squared minus 4, 3, divided by 3 minus 2 squared. So we are plugging all of these one by one. All of the test points in red, we're plugging them one by one in the first derivative because we are doing the first derivative test. We have 9 minus 12. That's going to be negative, divided by positive is negative. And we have another decrease. You see that? Consecutive decrease. And finally, the last value we are checking is 5. So f prime of 5, that's going to be 5 squared minus 4 times 5 divided by 5 minus 2 squared. which is 25 minus 20 is 5, so positive divided by positive equals to positive. So we have an increase at the end. We learned from the graph that 0, 0 is a max, and 4, 8 is, anyone with me? Min. I guess you're sensing how long this problem get to be, right? We still have second derivative test, and then we have to graph. Oops. Second derivative test. We take the second derivative and set it equal to 0. Oh, you can't do this in your notebooks? Yeah, I just copied it then. Now we set this equal to 0. Now look, it's cool because it's factored, so each one individually gets set to 0. So we'll get x squared minus 4x equal to 0, which will give us the same value as earlier. X is equal to 0, x is equal to 4. And then we have this other one. 2x minus 4 divided by x squared minus 4x is equal to 2 over x minus 2. Cross multiply. We get, oh, that's x minus 2 times 2. So 2 times x minus 2 squared is equal to 2 x squared minus 4x. So this equation should give us, right? Because we know these are critical points. It's the second one that gives us the inflection point if we have any. So that's going to be 2 times x squared minus 4x plus 4 is equal to 2x squared minus 8x. 2x squared minus 8x plus 8 is equal to 2x squared minus 8. That's not 8. There we go. I'm just solving the equation right now. These guys cancel. These guys cancel. 8 equals 0. That makes no sense, which means no inflection points. Because everything canceled, right? We know that 0 and 4. So do we do partitioning here if there are no inflection points? Do we? Yes. You partition over vertical asymptotes as well. So partitions are done either critical points vertical asymptotes or inflection points vertical asymptotes. We do not have any inflection points, but we do have vertical asymptotes, so we still have to partition and the vertical asymptotes. So boom, 2. Pick 2 values. Obviously, you can pick 0. Ooh, you can't pick 0. And you can't pick 4 either. Yeah, I'm not happy with this. 1 and 3. Let's check what's happening with concavity. And now we plug everything in a second derivative to see whether the value is larger or smaller than 0. If it's larger, it's concave up. If it's smaller, right? And look at the expression for second derivative. It's wonderful, right? And we can actually simplify it, because these guys cancel. These guys cancel, so it's 2 over x minus 2 minus, that cancels, 2x over 2 squared. Alright, that's the second derivative simplified version when you do the algebra. And now you can plug in number 1. So second derivative computed number 1 is giving us what? It's giving us negative 2 minus, computed 1 over here, 2 over, why do I have, oh, that's a square. So 2 over 1, so 2, which is negative 4, which means less than 0, which means concave down. And compute for 3. So 2 over 3 minus 2 is positive 1. And then we have 3, so that's a 6 minus 6. Negative, concave down. Awesome. We can maybe graph. So let's go all the way on the top. I know, solve one problem. That's why when someone in algebra complains after 5 steps, like, oh, it was terrible, you should just flip through your notebook and say, see, this problem took 3 pages.
This will be you in 2 years, right?
I'm sorry?
Like, go to high school, show them all this.
No.
Get them out of the math program while they still can.
Get them out of the math program? Oh, because, oh, you wouldn't be in a math program if you knew that this is coming up.
Exactly.
This is fun. This is like puzzles. You put it together, a little piece by piece, you know. So many, a lot of small pieces, you know, and then at the end, it's one big puzzle put together. Each individual piece you know how to do is just, I don't know, I never label this as hard. I label it as annoying, because it takes a long time. I'm sorry? Yeah, yeah. I know. So don't lose any pieces. That's why I said algebra, precalculus, YouTube. Yeah. I had no clue what I wanted to do. Oh yeah, go to 0, 0 and 4, 8. All right. 0, 0, 4, 8. We have 0, 0 to be what? Max. So I need to put my vertical asymptote at 2. This needs to be a max, so it's a frown. And this needs to be a min, so it's a smiley. Clearly, function has to follow the asymptote. And now look what's happening here. For concavities, this is concave down, this is concave up. It's already there. Done. You can graph without using calculator. How about you try one? You have the shopping list. X-intercept, Y-intercept, domain, and then first, second derivative test with derivatives. And you're done. Let's see. You're going to love it. Here. There's a lot of jokes going on. I just. What happened? Would I do what? Yeah, I'll move there. Let me just set up a problem. Something that would be easy to graph. Here, inverse tangent of x squared. You got this. I'll be back in 30 minutes.
Oh. The problem is you sit down and put it out. Hey, you're so out there. Yeah. So for the extra credit thingy, the replacement. No, yeah. I don't remember which I said we would grade, but like it was either 9A or 9B. One of them was the sine one, which I know I did correctly. And then the other was the tangent one, which while doing it, I knew I was going to correct. Can you just like, if I put the wrong one, I got the sorry. So it would be kind of a little bit. I mean, I'm getting the word. That one I know. Maybe there's like horizontal ones. Yeah, you should take a bucket. The thing is, oh yeah. He's also trading on the top of these. Yeah, people have. The reason why it's easy to take them down and reach them is because they're only strong enough to lift themselves. The drones are only strong enough to lift themselves, so if you can reach them, you take them down. At least the commercial ones. The commercial ones. I don't know about like military. Oh, that'd be awesome. Don't take Orgo.
You know what? I think I have the high school.
I don't know. I don't know what else to say.
What's your grade?
Well, you went for that. Well, I beat you in that.
There's only the highest grade in
Right,
our
Zach?
formula.
He's saying he would have the best grade in their class, and I'm like, well, me on that.
I don't know. True. Yeah. Well, I mean, they're like, in my defense, I did everything right. You know,
Whatever.
just accidentally made a mistake. Understandable, but we could.
We might have spent some better.
At least we didn't break the beaker like the other people did it. Is that your group?
I didn't do that though. That kid did.
The kid broke the beaker or something like that? Yeah. I got a whole it.
Oh, that wasn't us. No. We knocked over.
Yeah. I don't know. No,
It burst in his hand.
apparently he's holding it and then burst it.
He's a liar.
Yeah, we can
Are you talking about Anthony? Oh, that one. Skinny hair?
No.
Zach, you have to boss him up. Yeah. Knock him down.
I'm gonna make a boss out of
Who are you talking about?
organic coaching.
Organic chemistry?
Yeah.
Okay, that's good for you.
Not a whole lot of.
Joining
What is
the.
that you have there? You're gonna help me in that?
Yeah.
Can you help me understand it?
Yeah, that's why I'm here, so you can clearly say what I'm saying. No, clearly hear what I'm saying. That's what I wanted to say. I'm losing my mind.
We know.
I lost my mind like a week ago.
Ready? Let's take a look at this problem. So the first derivative, which would be f prime, is 2x divided by 1 plus x to the fourth. Would we all agree on that? Awesome. The second derivative is 2x over 1 plus x to the fourth. That's a terrible 4. There we go. And then we have 1 over x minus 4x cubed over 1 plus x to the fourth. And we can rewrite that one as 2 over 1 plus x to the fourth, then minus 2x minus 4x cubed over 1 plus x to the fourth squared. Oh no, that was wrong. I need to multiply them. That's 8x to the fourth. Much better. There we go. And now I'm multiplying 1 plus x to the fourth, 1 plus x to the fourth, there we go, which gives me the final version of the second derivative. That's going to be 2 minus 7x to the fourth divided by 1 plus x to the fourth, everything squared, which is what we don't care about because it's going to be 0. 6, yes. That's what I said. Please pay attention. Thank you. All right, great. So we have our function as tangent to the negative 1. So now we have our derivative, first derivative and the second derivative. Now let's work on everything else. X-intercept would be, we set y equal to 0, which means that the tangent inverse of x squared is equal to 0. You apply tangent to both sides. We get x squared is equal to tangent of 0. And then tangent of 0 is 0. So x squared is equal to 0 from where x is equal to 0. And it's giving us x-intercept 0, 0. If x-intercept is 0, 0, y-intercept must immediately be 0, 0. So we have x and y-intercept done. Next part is asymptotes. And for asymptotes, there are none, because inverse tangent as a function does not have asymptotes. Well, actually, it does have the pi over 2, but that's a horizontal, no vertical asymptotes. That's what I meant. So vertical asymptotes, none. Now, horizontal asymptotes. Then this is the trick. I'm going to draw inverse tangent, but this is the inverse tangent x. We are not sure if x squared changes this situation. So the best way to do this is to actually take the limit and see what's happening, right? So limit as tangent inverse of x squared as x goes to infinity. So positive infinity. You look at the positive infinity and you see that this infinity, it's still going to be pi over 2, but let's see how. So limit x goes tangent inverse of x squared. So now is equal to a question mark, a value. Let's put L, limit, capital L. There we go. So how you take this limit? You can write that L is equal to tangent minus 1 x squared, and then you apply tangent to both sides. You will see that it behaves the same way as if you had no x squared. Actually, maybe that would be easier to. Let's do by comparison. Let's do by comparison. Look, limit x goes to infinity of tangent minus 1x is pi over 2. This is what you are supposed to know from your precalculus trig class. So now if you compare this to the upper line, you see that this infinity went in there, and you got tangent inverse of infinity, which would not change at all if you take infinity and plug into the x squared, or x to any exponent that it's integer exponent like that. It would be an issue if it was 1 over x, or negative exponents, because in that case, it would be 1 over infinity would be 0, and then you would have inverse tangent of 0, which is 0. So that number would change. So just because of this comparison, we see that L is also pi over 2, so we still have our asymptotes at negative pi over 2 and positive pi over 2, because negative infinity would do the same thing. So horizontal asymptotes at y equal pi over 2 and y equal negative pi over 2. So this is the trickiest of all, the asymptotes, if you're not used to taking limits. That's the only thing. The rest should be straightforward. We have the first derivative test. We take our first derivative and we set that equal to 0. 2x over 1 plus x to the fourth equal to 0. Denominator drops, 2x equals 0, x equals 0. Right? Make sense? How do you sit? These are so small. These desks. All right. Copy of yours. Now, what do we have? We have The critical number at x equal to 0, we plug that in, we get y equals 0. So let's put f of 0 is 0. So we have 0, 0 to be min, max, or inflection point. We don't know yet. Min, max, inflection, we don't know. But we know it's the only point that partitions. We don't have no vertical asymptotes. So now, for our partition, 0 is the only one. And we have -1, +1. First derivative test, which means we are plugging these test points in the first derivative. So 2 times -1, 1 plus -1 squared. No, fourth. We're getting -2 divided by 2, which is -1, less than 0, which means decreasing. F prime at 1, 2 times 1, 1 plus 1 to the 4th is 2 over 2, which is 1, which is larger than 0. Oh, here. Closer. Makes more sense, right? And what I found is that we have 0, 0 is a minimum. Because that's how arrows aligned.
We're not done that, right?
No, we have the second derivative test. Imagine if there was a third and a fourth and a fifth. I mean, all of these, it just makes it more impressive. Yeah, I would go with the word impressive. You guys don't agree? What can I do? I think this is the correct, derivative. And now we set this equal to 0. Not a problem, right? Just 2 minus 6x to the 4th equal to 0. And we have something over here. 6x to the 4th equals to 2. X to the 4th equals to 1/3. And then finally, x is equal to plus minus 4th root of 1/3. Anytime you're taking the even numbered roots, like square root, 4th root, 6th root, 138th root, you have to put plus minus in front. Odd ones just preserve the sign that's there. So that's what we have. And that is the partition for our inflection points. Now we can figure out what that is. You know, you take the calculator and punch the numbers in. So when we do our partition, we are partitioning at negative 4th root of 1/3 and partitioning at positive 4 square root of 1/3. We are looking for a concave up, concave down business. And it has to be concave down, concave up, concave down, but let's see how. Because we already have the increase, decrease. But let's go. Second derivative, computed at let's pick points. So test points. -1 is good, 0 is good, and 1. So we're picking -1 first. So plug in -1, we get 2 minus 6 times -1 to the 4th divided by 1 plus -1 to the 4th, everything squared. Now, denominator is squared, so that's going to be positive at all times. We don't care about it. The numerator is 2 minus 6, which is -4. So the whole thing is negative, and there you go, concave down. Blessings.
Thank you.
Now, second derivative computed at the test point 0 is just 2 over the positive number, which is positive, so concave up. And computed at 1, it's as symmetric as the other one. I'll just put positive here, it doesn't matter. So it's -4 over positive, which is negative, another concave down. Yay! We have both of our tests done. And all I need to do now is to plug all of this on the graph. So I draw asymptotes. I will put 0, 0, which is a minimum, which means it gets a smiley face immediately. I will place these values, let's say there and there, for 4th root of 1/3. They should be much closer, but 4th root of negative 4th root of 1/3. And now he has to follow the asymptote, and he has to go to these 2 points. There is no other way than to go through the point and then bend out, go through the point and then bend out. So I hope that you guys see that after these points, this is concave down. Clearly in between is a concave up and then concave down. Observe that the function is perfectly decreasing all the way from left to 0, 0, and then it's increasing after 0, 0. So all of the aspects of the calculation are clearly visible on that graph. And we use those to come up with the graph. So that was me doing the problem from the student perspective, I guess. It's a procedure. It's a list of things. We haven't learned anything new in this section. You should know how to find x and y intercept. You should know how to find asymptotes from precalculus and from calculus, right? Sections 2, 4, 2, 5, or 2, 3, 2, 4, whatever. You should know, no, 2, 4, 2, 5. You should know how to do the first and second derivative tests from the section 4.2. You should know how to find min and max from section 4.1. What we did is we took all of these different sections and lectures across 3 different levels of math, and we put them in one section, created a shopping list of things that we have to accomplish, and once we find all of those little pieces, individual pieces, you just plot all the dots, and just like in a coloring book, connect the dots, except you don't have to color. So it's that much easier, right? And that takes care of this section. Now, anytime you see a problem, yeah, they look bad, but maybe they look bad until you take the derivative, just like this one. You remember all of the, when I said inverse tangent? But then you saw that the derivatives and stuff actually worked out very nicely. And this problem was not a big problem, right? Where the first one I tried actually turned out to be much worse. And I bet that you would rather go for the other one, right? That was really bad, and then we abandoned and switched. So this is our section 4.3. Next Saturday, we are looking into sections 4.4, 4.5, 4.6. We'll probably finish the half of the remaining material, chapter 4. So we're almost there. I think I'm going to see you another 8 times. That's it. 7? 7 times. And the class is over. So enjoy. We have to finish off this food, and I'll see you all soon. Look, 2 minutes over time. Wow, you're still here. Amazing. Bye, stream.